Alright, so this is the Honors Chemistry lesson video for section 5.2, and this is part 2. So in part 1, we talked about how to do the arrow electron configuration, which looked a little something like this. Like we'd start with 1s, 1 orbital, 2 electrons. Then we'd go 2s, 1 orbital, 2 electrons, like that. And then I taught you how to do standard electron configuration, where instead of writing the arrows, we would do powers. So like 1s2, 2s2, like that. As you can imagine, both of these get really long as you travel down the periodic table. So there is a third form of electron configuration, and that's called the noble gas configuration. So in writing electron configurations for large atoms, it's quicker to use the noble gas configuration. The noble gas configuration only indicates the noble gas before the element and the last incomplete energy level. Okay, so y'all, if we're all the way on row 5, or period 5, we already know 1s was filled in, 2s and 2p were filled in. We know all of those were filled in. So all we're doing is trying to show the ending of the electron configuration where it may not have already been all the way filled in. All right, so again, to keep it easy for y'all, I'm going to use my packet to see what the questions are on the next slides so that I can go back to that periodic table and label it for you. So if you don't have a periodic table labeled from the previous video, please make sure you do. S is the yellow, P is the red, D is the blue, and green is the F orbitals, or F sublevels. And so we have 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then remember P starts with 2. So we have 2p, 3p, 4p, 5p, 6p, and if you have anything down here, that's 7p. D starts with 3, so there's 3d, 4d, 5d, 6d, and then F starts with 4. So there's 4f and 5f. All right, so the first one that we're going to do is Y. Yttrium, which is right here at 4d. Okay, so again, normally we would go all the way to hydrogen and start at 1s. But I know that the first row is full because we're trying to get down here. I know the second row is full. I know the third row is full. And I know the fourth row is full. The fifth row is the only one that's not all the way full. So what I do is I find my element and I go to the noble gas. Remember, group 18 are the noble gases. The noble gas before the element I'm trying to do, not the one after, the one before. So see, I know all the way through 36, those rows are completely full. All I need to do is add my last few. Okay, so I start with krypton, Kr, and so you just put it in brackets. And so that's just showing everything on the first 4 rows is already full. And then I just start here and work my way to the element. So see how much shorter it is? So at RB, I am now at 5s. So I say, okay, I'm at 5s2, or sorry, I'm at 5s. I'm going to do 1 for RB, 1 for SR, so I'm going to do 5s2. And now I'm at Y, which is 4D. And I only need 1 to get through Y because it's the first element. All right, just like standard configuration, when you're done, you need to rearrange. All right, so see, I have 5s and then 4d, so I'm going to rearrange those. So I'm going to change it to 4d1, 5s2. Okay, and so that's all we're doing is you just start at the last full row and put that noble gas, and then just finish off the row that is incomplete. All right, so let's look at another one. So the next one is Ca, calcium. Okay, so I find calcium and I say, okay, what's the noble gas before it? So we know row 1's full, row 2's full, row 3 is full. So argon is the last noble gas before calcium. So again, once I start with argon, that's just showing me everything in the first 3 energy levels is full. So now I just have to go from here to calcium. Boy, that made it easy, huh? So at K, where am I? I'm at 4s. And then I need 1 for potassium, 1 for calcium, and so it's just Ar4s2. And that's all there is to it. Now, of course, some of them, they may be way over here, so you might have to go quite a few. So let's look at one that's just a little bit trickier than this, because they're not all this easy. All right, so our next one, it says Bi, but it also wants us to list the unpaired electrons. So I'm just going to leave myself a note so I don't forget to do it. All right, so we're doing Bi. So that's all the way over here. So this is the first time we are going to have to use the F sublevels. So let me show you where they plug in. All right, y'all, all you have to do is look at the atomic numbers. See how it goes 55, 56, 57, 72? Well, where is 58 through 71? It's right here. So this first F sublevel plugs in right here. And then here it goes 89, 104. So this second F sublevel plugs in right here. So in other words, I'm going to have to kind of go across here, then go through F, and then go back up here. Because remember, we're counting each element. And so we have to follow the atomic numbers. So that's the easiest way to do it. Okay? So, I find Bi bismuth. The last noble gas before it is Xe. So I know everything through my 5th energy level is totally full, but this row is not. Okay, so I start with my Xe, and then I'm just going to go over here and work my way from Cs all the way to Bi. But I can't forget that at this point I have to go down here. All right, so at Cs I'm at 6s, so I put 6s, and I do 1 for Cs, 1 for Ba, so I have 6s2. All right, now here's where it's going to get tricky. So I'm going to do it a weird way first, because it just depends on which element you're asked as to whether or not you need to actually do this. So now I'm at La, which is 5D. But y'all, this is where it gets a little weird. You actually fill in 1 in 5D, because notice I'm about to leave 5D and go to 4F. So instead, even though I know eventually I need to fill in all 10, for right now, I'm just going to put 5D1, because I realize I'm going to head down here. Because the thing is, if I ask you one down here, you never go back up to 5D, so you wouldn't have 5D10. Okay, so for right now, I'm just going to put 5D1. I will go back and fix it in a minute, okay, because I'm going to follow my atomic numbers. So see, I'm at element 57, and I'm not going to go across any more than that right now. All right, now I need to go to element 58, which is Ce, so I'm at 4F. And I'm going to go all the way across, because see, I'm trying to get to number 83. I'm going to go all the way across to 71. This is 14 elements. If you go back to your chart, it'll say F holds 14. I'm not going to count for you. You can count on your own. All right, so 4F14, so I made it to element 71. So now I'm going to go back to 72. All right, so now I need to add 1, 2, 3, 4, 5, 6, 7, 8, 9 more to D. So now it becomes 5D10. Like I said, y'all, sometimes if I ask you one down here, you don't make it back to 5D. So go ahead and get used to putting 1 in there and then go back and add the rest if you need them. All right, so that got me through Hg. So now I'm at Ti, so I'm at 6P. And I need 1, 2, 3. And so then there's my answer. However, what's wrong with my answer? I didn't rearrange it yet. Okay, so when you get near the bottom, they're all out of order. So we got 6s2, 5d10, 4f14, and 6p3. So I need to move my 4f first, then my 5d, then my 6s, and then my 6p. Okay, so let me go ahead and do that real quick. So 4f14 and 6s2 need to swap places. So see, now I have 4, 5, 6, 6. All right, so this is my final answer, but then it asked me about unpaired electrons. Well, I didn't do the arrow configuration for this. Okay, this one's full, this one's full, this one's full. Whenever they're full, all the electrons are paired. This is not only one that's not full. So what would 6p look like with 3 electrons? Well, we know they would rather be separate than together, so it would look like this. So there would be 3 unpaired electrons. Remember, any sublevel that's full, they're all paired, because you'll have one up and one down. Okay, so you only need to check any less than full sublevels. Alright, so hopefully you're finding noble gas configuration pretty easy. A lot of my students, once they know about noble gas configuration, they don't want to do any of the other ones because they're longer. Alright, so I'm going to give you a couple to try. So remember, you're trying noble gas configuration. And so the first one you're going to try is Fe. Alright, so right here. So pause it, try it. I'll assume you've done that at this point, and we'll look at it together. Alright, so Fe is right here. I know that my first 3 energy levels are full, so I'm going to start at AR. So everything through here is full, and then I'm just going to finish off this row. So K is at 4S, and I'm going to do 1 for K, 1 for Ca, so 4S2. Now I'm at SC, we're at 3D. It can hold 10, but remember I'm stopping at Fe. 1, 2, 3, 4, 5, 6. So I'll put 3D6. And then the last step is, of course, get it in order. So 3D6 needs to come before 4S2. And so there you go. And that's all you have to do. So hopefully you got that one right. So let's look at another one. And remember, make sure you're trying these. Watching me do it does not help you learn a lot of stuff. All right, so try Si. So it's right here. So I will assume you paused it and tried it, and let's look at it together. All right, so I go to the noble gas before Si, and I know that energy levels 1 and 2 are full. And so I'm going to start with neon, saying everything neon through hydrogen is full. So then I come over here, I'm at sodium, which is 3S. And I'm going to put 1 in for Na, 1 in for Mg, so 3S2. Now I'm at aluminum, which is 3P. I put 1 for aluminum, 1 for silicon, so I put 2 in there. And then in this case, I'm already in order, so there's no rearranging necessary. All right, so hopefully you got that one right too. If not, you got one more chance to get one right. All right, so the last one I want you to try is K. This one should be super easy. All right, so I'll give you a chance to try K. I'll assume you have already tried it. So for K, the noble gas before it is argon, Ar. So everything through the 3rd energy level is full. So now I need to jump down. So K is at 4S. And then because K is the first element in 4S, I just need a 1. So my electron configuration, my noble gas electron configuration for Kr is just for K is just Ar4S1. And that's noble gas configuration. All right, so before we move on to quantum numbers, we need to focus on a few exceptions to the rules for noble gas configuration. For all electron configuration, not just noble gas. And I'll probably have to come back to this slide, so just bear with me. All right, so that we did all that, got all this done, got our noble gas. So here we are, exceptions to the rules. So sublevels are the most stable if they are all the way full. However, they're still pretty stable if they're half full. The problem is when they're not either all the way full or half full. So like a P sublevel can hold 6. So it's incredibly stable with 6. It's still really stable with 3. But if it has like 1, 2, 4, or 5, it's not as stable. This causes electrons to jump to different sublevels to make the atom more stable. The jumping does not happen until the 3rd energy level, because remember how we talked about the energy levels get closer together as we get further from the nucleus. So until the 3rd energy level, they're just not close enough for the electrons to make that jump. Now there's only 2 exceptions you need to memorize. There are way more than 2 actual exceptions. There's only 2 that I will actually ask you about that you need to know by heart. All right, and so those 2 are chromium, which is Cr on the periodic table, and copper, which is Cu. Okay, so I'm going to go back to my periodic table so we can look at Cr and Cu real quick. Okay, so the first one says, write the standard electron configuration for Cr. So remember, I have 1s, 2s, 3s, 4s, 5s, 6s, 7s. I have 2p, 3p, 4p, 5p, 6p, possibly 7p. I have 3d, 4d, 5d, 6d, and I have 4f, 5f. All right, so we have Cr right here. We're just writing standard configuration, so we're going to go all the way back to hydrogen. So hydrogen is 1s. There's 2 for hydrogen helium. Li is 2s. There are 2, LiBe. I'm going to assume at this point you kind of got it. 2p for B. We're going to fill in all 6. For Na, we're at 3s. I'm going to do 2 for NaMg. For aluminum, I'm at 3p. I'm going to fill in all 6. For K, I'm at 4s. I'm going to fill in 2, 1 for K, 1 for Ca. And then at Sc, I'm at 3d. And I don't need all 10, I just need 1, 2, 3, 4. So if you look, everything up to 3d is full, so they're all stable. However, 3d is not full, it's not half full, but it's close to half full. Because of course a D sublevel to be half full needs 5. Alright, so before we start moving anything around, let's rearrange so we don't forget. Okay, so I can see 4s and 3d need to be rearranged. So I'm going to move 3d4, 4s2. So again, 3d is the one that's not stable. So what happens is one electron from 4s leaves and goes to 3d. So see, now 3d is half full because it has 5. 4s is still stable because s only holds 2. So if it has 1, it's half full. If it has 2, it's full. So it's stable either way. So it doesn't mind giving one of its electrons to 3d. So this is the actual ending of chromium. You have got to remember the exception. If you put 3d4, 4s2, I'll mark that wrong. I don't even give partial credit for it. So make sure you know this exception. A very similar thing happens with copper, which is Cu. Okay, so let me erase this one and show it to you. So these are the first 2 exceptions on the periodic table. That's why those are the ones you need to know. However, like I said, there are more. But please don't try to make up your own, because sometimes you think you're making up one that's right and it's not. Okay, so only do the exceptions for these 2. If I give you another one that's an exception, then I'll let you know what it is. All right, so for copper, we start at hydrogen. Oh wait, let me make sure we're doing the standard, or are we doing the arrow? Let me check my PowerPoint. It looks like we're doing standard. All right, so at hydrogen, I'm at 1s2, hydrogen helium. At lithium, I'm 2s2, LiBe. For boron, I'm 2p6. For Na, it's 3s2, NaMg. For aluminum, it's 3p6, because I'm going to go all the way across. For K, it's 4s2 for K and Ca. And then Sc is 3d, and if you count across, it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so again, 3d is the only one that's not stable. It's not all the way full, it's not half full, but it's almost all the way full. So let's rearrange first. So I'm going to put 3d9 first, 4s2, and see y'all, the same thing is going to happen. To get 3d to be stable, 4s is going to give one of its electrons to 3d, so 3d can be stable. All right, so copper actually ends in 3d10, 4s1. All right, so like I said, y'all, there are more than 2 exceptions on the periodic table, but these are the only 2 you need to know. Like I said, if I wanted you to discuss another exception, I would give you the electron configuration. All right, so let's move back to where we were in the PowerPoint. All right, so then there's chromium. Then we rearrange it and give that electron. And so remember, don't make up your own exceptions. Just do this for CR and CU. Or I might ask you to predict what an exception would be. In that case, you know, you can come up with something. All right, so section assessment. If it's just verbal, like I said, I'm just going to say it and move on. So what are the 3 rules for writing electron configuration of elements? Aufbau's principle, Pauli exclusion principle, and Hund's rule. Aufbau principle, Pauli exclusion principle, and Hund's rule. So explain why the actual electron configurations for elements differ from those assigned using Aufbau's principle. All right, so remember, as we get farther from the nucleus, the energy levels get closer together, and so that's when those exceptions start happening, and the electrons might change sublevels. Okay, so as we get farther from the nucleus, energy levels get closer together, and so then the electrons might change sublevels to help for stability. That's what we're looking for here, is stability. All right, so it says arrange the following sublevels in order of increasing energy. Okay, so y'all, the periodic table is already set up in increasing energy. So like 1s is the lowest energy, 2s is next, 2p is next. So let's just get these in order. All right, so out of all of these, our lowest energy would be 2p. All right, next would come 3s, then would come 3p. All right, technically on the periodic table, 4s comes next, and then 3d. Okay, so remember, you are just following the order of the periodic table. Now, of course, we rearrange these when we're done, but energy-wise, 4s still comes before 3d. Okay, we rearrange them for the purpose of ions, which I'll show you in chapter 7. All right, so number 4, why does one electron in a potassium atom go into the 4th energy level instead of squeezing into the 3rd energy level along with the 8 already there? Well, y'all, when we say they hold a certain amount, they cannot hold more than that. So if the previous energy level is already full, there is no squeeze another electron in there, it's already full. So you move on to the next energy level. Okay, so you can just say the 3rd energy level is already full, so the electron has to go in the 4th one. Like I said, there is no squeezing one in there. That's not a thing that happens. All right, so let's move on to something I super love, and that's quantum numbers. So quantum numbers are a set of 4 numbers that can describe any electron. So you could literally give me 4 numbers, and I'll know exactly what electron you're talking about. You don't have to give me any explanation. So the 4 numbers are represented by letters N, L, M, and S. So N represents the principal energy level. So it's going to be a 1 through 7. L represents the sublevel. So if it's an S sublevel, we give it the number 0. P is 1, D is 2, F is 3, and G is 4, although we don't have enough elements to get to G yet. M represents the orbital. Whoop, and I see that my dashes have disappeared. So here, let me add some dashes on here. So your orbitals are always set up like a number line. The middle orbital is 0, and then to the left you go negative, to the right you go positive. So since S only has 1 orbital, it's 0. P, the middle one 0, negative 1, positive 1. D, the middle one 0, negative 1, negative 2, positive 1, positive 2. F, the middle one 0, negative 1, negative 2, negative 3, positive 1, positive 2, positive 3. And then the spin is the S quantum number, and it tells is the arrow up or down. So if the arrow is up, it's positive 1/2. If the arrow is down, it's negative 1/2. Okay, so y'all, before you think, oh my gosh, this is confusing, it's really not. Okay, so let's say I have 2p right here. Okay, the N represents the number. This would be my N. The P, that is a P. The L represents the sublevel. Let's say I'm asking about this electron right here. The M represents the orbital, and the S represents the spin. So let's just look at the 4 for this one. So N would be 2, because it's in the 2nd energy level. P is 1. Remember, S is 0, P is 1. So because it's P, my second one will be a 1. Remember, M is the orbital, so I'll put 0 for the middle one. This is negative 1, this is 1. So since I'm looking at this electron, I would put a positive 1. And then the last one, S, is the spin. Since I picked the down electron, I would do negative 1/2. That's all we're doing. Okay, so let's look at some more examples real quick. Okay, and I don't even know, that's barely legible, but you know. All right, so it says write the quantum numbers for the following electrons. Okay, so I have 3 that are different colors. So we have a green, a blue, and a red. So let's just start with green. So if you can't see well in the video, it's the down arrow in the first orbital of 2p. Okay, so remember, my N number is just the energy level. So y'all, you're just going to look at the number. So it's 2p, so my N is 2. The next letter represents the sublevel. S is 0, P is 1, D is 2, F is 3. So since it's 2p, it's a 1. The next one represents the orbital. So remember, I put a 0 in the middle, negative to the left, positive to the right. So since it's this electron, I'm going to put a negative 1. And then the last is the spin. So since my arrow is down, I'm going to put negative 1/2. Just like that. That's all you have to do. Super easy. I love quantum numbers. Like, it's easier than me having to be like, oh, okay, it's like the down electron in the first orbital of 2p. Like, instead of having to verbally say all that, you can just say the 4 numbers. All right, so next let's look at this blue one right here. All right, so it's in 3p. So my N quantum number is 3 because I'm in the 3rd energy level. My L quantum number for P is a 1. Remember, S is 0, P is 1, D is 2, F is 3, G is 4. My M is the orbital. So remember, 0 in the middle, negative to the right, positive to the left. So since it's in the middle, I would put 0. And my last one is the spin. So since I picked an up arrow this time, it would be positive 1/2. Okay, so this was negative because it was down. This one's positive because it's up. And you don't have to actually put the positive. I just put the positive. All right, and then our last one is our red arrow right here. So here I'm in 3D, so my first quantum number is a 3. I'm in a D sublevel, so remember, for L, S is 0, P is 1, D is 2. And that's the thing you gotta remember is S is 0. A bunch of people want to put S at 1 and then they think D is 3. But S is 0, P is 1, D is 2. All right, for my M quantum number, I set up a number line, 0 in the middle, negative to the left, positive to the right, so I'm in the -2 orbital. And then last is the spin. Since I picked the up arrow, it is positive 1/2 again. Now, a lot of you can do it correctly if I give it to you like this, like I have the electrons drawn for you, but a lot of times I'll just specify kind of which electron I want you to do, and that's actually what you have trouble with, is figuring out what electron I'm talking about. Mainly because I'm not giving you the quantum numbers, which would clearly tell you which one. All right, so let's move on. Okay, so I'm going to show you how to do the top one, and then I'll let you try this one. All right, so this says the last electron in Mn. So y'all, if you look at a periodic table, I'm not going to click all the way back. If you look at a periodic table, Mn is in the 3D sublevel. Okay, like you can see, it's a little bit after Sc. So I know that the last electron is going to be in 3D. So see, I don't have to draw the entire electron configuration to know where the last one is. So how many electrons would go in 3D? Well, if you count across to Mn, there's 1 for Sc, 1 for Ti, 1 for V, 1 for Cr, 1 for Mn. So I need 5 electrons. They would all be separate, not together. And so this is the last one I would fill in for Mn. Now, if you have to start at 1s to get all the way here, that's fine too. But yeah, if you can just start at the last sublevel, that's the easiest way to do it. All right, so I have this electron. So of course, my first quantum number is a 3 because I'm in the 3rd energy level. My second quantum number is a 2 because remember, S is 0, P is 1, D is 2. My third one for the orbital, I set up a number line, 0 in the middle, -1, -2, +1, +2, so I'm in the +2 orbital. And then the last one is the spin. I picked an up arrow, so it's +1/2. All right, so maybe you try the next one. So I've asked for the 6th electron. So yeah, just fill in order until you get 6 electrons, and the 6th one is the one I want you to do the quantum numbers for. All right, so pause it, try it, and then I'll assume you've done that. So I need the 6 electrons. So I know 1s holds 2, I know 2s holds 2, and I know 2p can hold 6, but I only need 6 electrons. So see, I have 1, 2, 3, 4, 5, 6. Okay, remember to follow Hund's rule. So I'm literally asking you about this electron right here. So we write quantum numbers. So it's in 2p, so my first quantum number, N, is 2. P is my sublevel, so remember S is 0, P is 1. For the M, I look at the orbital. Remember, 0 is in the middle, negative to the left, positive to the right. So I'm in the 0 orbital. And then I picked another up one, so it is +1/2. Okay, so this is the way I will more commonly ask instead of me giving you the electron configuration in circle. Mainly because I can't do that very easily on a computer. So see, quantum numbers are super easy. I really like them. All right, and so then this is just my answers. There we go. All right, is there anything? Oh, there's a little bit more. So let's look at some questions. So it says, predict the number of subshells in the fourth shell, n equals 4. Okay, so y'all, the n number tells me how many sublevels. Like the first energy level, 1, has 1 sublevel, S. The second energy level, 2, has 2 sublevels, S and P. The third one has 3, S, P, D. The fourth one has 4, S, P, D, F. So because it's energy level 4, I know there are 4 sublevels. So it says give a label for each of these. Well, there's going to be an S, P, D, and F. So there will be 4S, 4P, 4D, and 4F. Then it says how many orbitals are in each of these sublevels. Okay, well 4S has 1 orbital, 4P has 3, 4D has 5, and 4F has 7. Remember, the number in front does not change how many orbitals a sublevel has. The letter indicates that every time. All right, so let's move on. All right, so the next one, it says, what is the designation for the subshell with n equals 5, L equals 1? Well, if n equals 5, I know it's going to be 5 something. If L equals 1, remember, for L, S is 0, P is 1, D is 2, F is 3. So since it said L is 1, I know that's 5P. How many orbitals are in the subshell? Well, every P sublevel has 3 orbitals. Then it says indicate the value of M for each of these orbitals. So remember, M is where we would have our 5P, our 3 orbitals. Remember, the middle one's 0, to the left is negative, and to the right is positive. So it would be -1, 0, and 1. All right, so that is how to do noble gas electron configuration and how to do the exceptions for copper and chromium. And then lastly, that is quantum numbers. So hopefully you like quantum numbers and electron configuration as much as I do.